Hey everyone, here's the Unit 13 review. We're going to start out by looking at the problems that you would have the graphing calculator for on the test, and we're going to switch over to the ones that you cannot have the calculator for. So on this number one, we have log base 3 of x to the 5th equals 2. I'm going to start out by rewriting this as an exponential equation. And so I always start at my base, raise it to this power, it will equal whatever's sitting right here. So I have 3 squared equals x to the 5th. I'm solving for x, so to get x by itself, I could take the 5th root of each side, or, in other words, raise each side to the power of 1/5. 1/5 is the same thing as the 5th root. I chose that because 5 times 1/5 will cancel out, and so now we have 9 to the 1/5 will equal x. So in your calculator, you would type in 9 to the power of 1/5, and you get 1.55. We'll leave it at 2 decimal places. So 1.55, so there's our answer. X equals 1.55. Let's look at the next problem. So we have 1/8 to the negative 3x equals 32 to the x minus 2. So if you've done enough of these problems, you would first look to see, okay, can I make my bases the same here? Usually those are your two options, like number 1 where we rewrote it, we switched the forms, or number 2 here where we can make the bases match. Well, I know that if I ignore that 1 over for just a second, if I just look at the 8 and the 32, I know that those are both powers of 2. So I'm going to change this 1/8 to something of 2 to the something power. To get from 2 to 8, I would cube it. So 2 to the 3rd is 8, but 2 to the negative 3 is 1 over 8. Leave the other exponent there. Also rewrite the 32. Well, 2 to the 5th power is 32, so you have x minus 2. When you have an exponent to an exponent or a power to a power, you multiply those together. So you'll have 2 to the 9x equals 2 to the 5x minus 10. Once your bases match, you can ignore them and just use the exponents. So we'll have 9x equals 5x minus 10. Subtract 5x from both sides, so you get 4x equals negative 10. And x equals, when you divide both sides by 4, negative 2.5. So we didn't even need the graphing calculator for this one. By the way, notice that the instructions said solve algebraically, but with a graphing calculator, you should get as far as you can without the calculator before you plug anything in. So you see we didn't even need it there. Number 3, log of x minus log of 4 equals 2. So I've got same bases being subtracted, so always combine things if possible if it would make it simpler. So I'm going to have log of, when I subtract, I combine them by dividing. So I'll have x over 4 equals 2. Okay, so there's nothing else I can really work with, so let's try switching the form. So if my base is 10, remember that I go from the bottom number raised to this power equals what's on the inside. So I will have 10 squared equals x over 4. Well, 10 squared is 100. So I have 100 equals x divided by 4. Therefore, x will equal 400. Number 4, I've got 8 to the x plus 3 equals 200. I can't make these bases look the same. 200 is not a power of anything shared with 8, at least as far as I'm thinking of right now. So when I can't do anything else, try switching the form. So I will have log, my base is 8. So log base 8 of 200 equals x plus 3. So notice we're still doing that same pattern we did before. So log base 8 of 200 equals x plus 3. To get x by itself, we're going to have to subtract 3 from both sides. We'll have x equals log base 8 of 200, and then we'll subtract the 3. So this is where we switch over to the calculator, and we'll type in. So we'll go to the log, so that's control this 10 to the x. That'll give us a log. So we have log base 8 of 200, then go out of the parentheses, then the minus 3, and we get negative 0.45. So x equals negative 0.45. Number 5, ln of 4 plus ln of 2x equals 6. Just like we can combine the problems like in number 3 where we had log, we can also combine the ln because that's just log base e. It's just log with a different kind of base, and so short for that would be ln. So I'm going to have ln of, when I combine these, since there's addition here, I will multiply them. So ln of 8x equals 6. Okay, when you get stuck, try switching the form. So this is log base e. So my base is e to the 6th. So e to the 6th equals 8x. So x will equal e to the 6th divided by 8. So in your calculator, the e is in this little pi button here, so I'll have e to the power of 6, and then divided by 8. We get 50.43. So x equals 50.43. Number 6, negative 6 plus 3 ln of x equals 3. I'm going to start out by adding 6 to both sides to get this 6 out of the way. So I'm going to have 3 ln of x equals 9. Well, I can divide both sides by 3, so I've got ln of x equals 3. Now if I want to rewrite this, remember this is log base e, so I'll have e to the 3rd power equals x, so e cubed equals x. And so then in the calculator you would type in e cubed and you get x equals 20.09. Number 7, we got e to the power of ln of x to the 4th equals 16. Remember, this is log base e, so when you have e to the power of a log base e, basically it cancels. But make sure that there's nothing sitting in front of the ln as seen here. For example, if that 4 had been in the front, you would want to move it back over as the exponent first, so that way it looks like what we have now, what was given to us. Then the e and the ln would be next to each other. You cancel that out. So this is x to the 4th equals 16. Then you take the 4th root of both sides and you'll get x equals, this 4th root of 16 is plus or minus 2. It's always a good idea that whenever you have an x that was originally in a log, that if you plugged it back in, that it would not make you have the log of a negative number. Well, if I had the log of negative 2 to the 4th, well, negative number to an even power, such as the 4th, would be positive, so it doesn't affect it here. So our answers are plus and minus 2. Okay, so now we're going to look at some inequalities and applications that you will have a graphing calculator for. You can solve by graphing or on the calculator or by hand, algebraically. So let's just go ahead and look at the calculator. So we've got 5 ln of x is less than negative 1/2 x plus 1/2. So let's switch over to the calculator. Well, before we do, let's talk about one thing. We're going to put the left-hand side in as one thing and then the right-hand side in as another. So we're going to have two different functions. This left-hand side will be one function and this will be the second function. Okay, so switching over to a graph. So we'll have 5 times, ln is above that e to the x. So we're going to go control, there we go, ln, so we'll have of x. So there's that left-hand side. And then hit tab to get another line. So then the next function will be our right-hand side, which was negative 1/2 of x. So 1/2 of x, and then plus 12. So I may need to move the screen around a little bit to see both of our functions. So in green we've got the negative 1/2 x plus 12, and in red we've got the 5 ln of x. So of course we're going to look at the intersection by going to Menu, Analyze Graph, Intersection. Click on the left and the right, and we have 6.03. So remember originally it said, where is 5 ln of x less than this other part here? So we're looking for where are the y values less than the green. So where's the red line less than the green line? And that is for the x values that are less than 6.03. So we know that the x values have to be less than 6.03, but as far as a lower bound, looking at this function, remember that we cannot take the log of a negative number, so x cannot be negative. So x also has to be greater than 0. So our solution would be 0 is less than x is less than 6.03. By the way, it's not going to be equal to for the 0, because I can't take the ln of 0. And here we don't have the equal to the 6.03 because originally the sign was just a less than. It was not an equal to. Number 9, we have 2 times log of 10x is greater than 3. So again, just since we're here, we're not going to take the log of a negative number, so we need to make sure 10 times what? We need to make sure that that thing stays positive. So again, x will have to be greater than 0. But let's switch over to the calculator. So for the first function, we'll type in the left-hand side, which was 2 times the log base 10, but I don't have to fill in the 10 of x, and then the right-hand side was 3. So I'm going to look at the intersection. So I'll get Menu, Analyze Graph, Intersection, and I get 3.16. This time we were saying, where is this log greater than 3? So where is this red line above the 3? Well, that's as long as the x values are bigger than 3.16. That will keep the top part of the red line. So we just saw that x has to be greater than 3.16. But notice we had talked about the x being greater than 0. Well, since we found out that our answers have to be greater than 3.16, we don't really need that the x is greater than 0. It was just something to remind ourselves of. So this is really all that we need right here. Sue invests $8,000 at 6.27% interest compounded continuously. How long will it take for the investment to reach $20,000? Compounded continuously tells us that we're going to be using this A equals PE to the R times T. Okay, so A is our final amount, so that will be the 20,000 equals P will be our initial amount, which is 8,000. Then we have E to the rate of 0.0627, that's 6.27 in decimal form, and times T. So we're needing to solve for T. So I'm going to divide both sides by 8,000 to get that out of the way. So I'll get 2.5 equals E to the 0.0627 T. And then if I rewrite this as a log, I would have log base is whatever has the exponent, so log base E of the opposite side, so 2.5 equals, the log is equal to the exponent, so 0.0627t. And then to get t by itself, we will divide both sides by the 0.0627. So I'll get t equals, log base E is just ln, so let's shorten that a little bit. So ln of 2.5, and we're dividing that 0.0627. This is where we will type it into the calculator. And when we do, we will get that t equals 14.61 years. Number 11. A paleontologist uncovers a fossil of a saber-toothed cat. He finds a specimen has 15% of its original carbon-14, which has a half-life of 5,730 years. How old is the fossil? So maybe you noticed on the worksheet that you got in class that there's another formula for half-life, and it's this. We've got A equals I. So A is the final amount, I is the initial amount, times 1/2 to the power of T over the amount of how long the half-life is. So using this formula here, we're looking for how old it is. So we're looking for the time. And so currently it has 15% of its original carbon-14. So that would be 0.15 equals, of course at one point it had 100%. Then we've got 1/2 to the power of T, which is what we're solving for, over the half-life is 5,730 years. So now we need to work with this a little bit. I'm going to rewrite this as a log. So I'm going to have log base 0.15 of, by the way, this 1 times anything that doesn't matter, so really when I'm rewriting this I've already ignored that. So log base 0.15 of, oh dear, that was wrong. Log base, clearly my base is 1/2. Log base 1/2 of 0.15 equals T over 5,730. So then at that point we can take T by itself, because I will multiply both sides by 5,730. And when I do that, let's write this out first. So log 1/2 of 0.15. I can go to my calculator and type it in. So I'll have 5,730 times, I'll hit Control to get to the log, base 1/2 of 0.15. Hit enter, and I get 15,682.8. So the fossil, as we just discovered, is 15,682.8 years old. Number 12, Bob bought a boat in 1993 for $20,000, and it has decreased in value by 6.85% each year. What was the boat worth in 2006? Okay, so that's the formula. A equals B times 1 plus or minus R raised to the T. Okay, so we're looking for what was it worth in 2006. So that'll be our final amount. Our initial amount was 20,000. We have 1. It's decreasing in value, so that means we're going to have 1 minus that rate of 0.0685. And it did give us the time. So our time here, let's see, if we bought the boat in 2006, or in 1993, but it's now 2006, the difference in that is 13. So our time is 13 as well. Then we just plug that into the calculator, and when we do, we'll get the amount is 7,950.73. Okay, so that's the end of the calculator part, the graphing calculator part. By the way, be sure to look over exponential and logarithmic applications worksheet, that long worksheet front and back that has word problems and the solving problems, which is on the back, solving logarithmic equations worksheet. For additional examples, each of those problems is going to be a good practice for you for the test. Now let's go on to the non-graphing calculator portion of the test. And here we are. So no graphing calculator, just a lot of algebra. That's okay, we can handle it. So log base 4 of 8 plus log base 4 of 32. We have like bases of 4, we're adding, so we can combine it into a single log by multiplication. So that 8 times the 32 is 256, and we think 4 to what power gives me to 256? Well, 4 to the 4th power is 256, so there's our answer. 14, log base 3 of 75 minus log base 3 of 25. So we have like bases of 3. This time we're subtracting, so we can combine it into a single log by division. So log base 3 of 75 divided by 25 is 3. Now we think 3 to what power equals 3? 3 to the 1st power equals 3. So we're done. Next problem, log base 16 of 4 to the 2x. There's a couple of different ways you could think about solving this. One way would be, if I have an exponent behind a log, I can move it to the front. So I have 2x times log base 16 of 4. So I have the 2x in the front, and 16 to what power gives me 4? Well, 4 is the square root of 16. So a square root in exponent form would be 1/2. So 16 to the 1/2 gives me 4. So this in the end, 2x times 1/2 equals x, and that is the simplified expression. Log base 6 of 6 to the 5th. Okay, to simplify this one, you can know what the answer is instantly whenever you have a log of a base that matches what it's being taken of. So log base 6 of 6, that just equals 1. So in a roundabout way, that cancels. But if you're wanting to remember why, remember an exponent you can move to the front. So you have 5 times log base 6 of 6. Well, that thing just equals 1. So here we have 5 times 1, which is just 5. But if you want to take the shortcut of it, instead of writing it out, log base 6 of 6 cancels out to 1, so you're just left with that exponent of 5. Number 17, 3 to the log base 3 of 4x. Again, 3 with an exponent of log base 3, essentially it'll cancel and you'll just be left with a 4x. And it's a weird way to think about it, because in the exponent you're thinking 3 to what power would give me 4x? Well, that would give you an exponent that then you would put on the 3 and it would still give you the 4x again. Shortcut, 3 to the log base 3 cancels. You're left with the 4x. By the way, that is different than 3 times log base 3 of 4x. That would not cancel. It's only whenever that log is in an exponent up here. So that would have to be in your exponent in order for it to cancel. So don't do that right there, okay? Only here. Next problem. Okay, so again, log base 232 to the 6. I've got an exponent, I'm going to move it to the front. So I've got 6 times log base 2 of 32. And I've got the 6 times 2 to what power gives me 32? Well, that's 5. So 6 times 5 is 30. So you can see how quickly these problems go. Number 19. This one looks a little bit different. I've got log base 3 of 1 over 3 to the 5th power squared. So I'm going to go ahead and take that 2 to the front like I've done before. So I have 3 to what power gives me 1 over 3 to the 5th. Well, if I ignore that 1 over part, and I say 3 to what power gives me 3 to the 5th, well, that would be 5. But we know to get 1 over that would be a negative exponent. So log base 3 of 1 over 3 to the 5th is negative 5. Don't forget that 2 in the front. So 2 times negative 5 is negative 10. There's our final expression. Okay, ln of e to the 2x plus 6. So we just talked about if we see something like log base 3 of 3 to the x, that thing would cancel and you'd just be left with x. Well, ln, remember, just log base e. So if you see something like this, log base e is just ln. So that would cancel. So ln and e cancel each other out, and you're just left with the 2x plus 6. 21. Log base 8 of 1 over 64. So I'm thinking this is log base 8 of, so 8 squared would get me to 64, but 8 to the negative 2 would get me to 1 over 64. So log base 8 of 8 to the negative 2 is equal to negative 2. I know that looks a little different than how I've written it before, but that's just another way you can look at it. 8 to what power gives me 8 to the power of negative 2. So that negative 2 right there. All right. Oops. ln of 1 or log of 1. For each of these, this first one I've got log base e of 1. So e to what power will give me 1? Well, anything raised to the 0 gives me 1. And same thing here, I've got log base 10 of 1. 10 to what power gives me 1? 0. So basically, if there is a 1 sitting right here, that means it's just 0. Number 23, solve for x. Log base 5 of x minus 2 is less than or equal to 3. I'm going to start out by rewriting this as an exponent. So my base is 5. So if I have 5 cubed will be on this side and the x minus 2 will be on the other. But since we are switching from log form to exponential form, that's the inverse, so I need to change the direction of the sign. 5 cubed is 125. And then if I add 2 to both sides, I'll get 127 is greater than or equal to x. But I'm not done, because remember, we can never take the log of a negative number. This thing right here cannot be negative. So x minus 2 has to stay positive. It has to be greater than 0. So x must always be greater than 2. So I need to combine this and the 127 into one statement. So I'll get 2 is less than x is less than or equal to 127. Okay, let's fill in these blanks. I've got f of x equals negative e to the x plus 2 minus 4. And we want to figure out the domain, range, and asymptote. Okay, so I've got e to the x plus 2. This is an exponential function. And remember, the parent function roughly looks like this. Okay, where its domain was all real numbers. Its range was y is greater than 0, and its asymptote was at y equals 0. And that's just true for any of our exponential parent functions. So, looking at this, moving left or right won't affect the fact that the domain is still all real numbers. However, the range is going to change a little bit because it used to be y is greater than 0. However, we've moved down 4, so the y values are going to have something to do with that negative 4. But notice that we've reflected it over the x-axis, so it will be y is less than negative 4. And everything moved down 4, so the asymptote is also moved down 4 as well, so it's going to be at y equals negative 4. So the fact that it was exponential told me that it was going to be all real numbers, and the fact that it moved down 4 gave me information about the range and the asymptote. However, on 25, we've got 2 times the ln, or the natural log, of x plus 1 plus 3. So remember that log functions, the parent functions, were the reflection of the exponential over that line y equals x. So the domain was x is greater than 0. The range was all real numbers. And the asymptote was at x equals 0. And that was true for any log parent function. So on the domain, I have moved to the left one. So the domain will have moved to the left one as well. So what used to be at 0 is now going to be greater than -1. The range was all real numbers, and stretching it and moving it up 3 will not change the fact that it's still all real numbers. And the asymptote, since we moved to the left one, the asymptote that was at x equals 0 is now at x equals -1. So the range came from the fact that it was a log function, and then the domain and the asymptote came from the left and right shift of our graph. Okay, we've made it to the last problem. Identify the parent function. So we've got A, B, C, and D here, and this won't all fit on the screen at once, so just kind of remember which one was which here. So on this first one, notice that we have a vertical asymptote. So right away, because there's a vertical asymptote, which kind of parent function has a vertical asymptote? So we've got an exponential, a quadratic, a square root, and a log. Remember that L reminded me of a vertical line, so this is a log function, so its parent function is log base c of x. Number 2. So you can see we have a horizontal asymptote, and when x is 0, y is 1. That to me sounds like an exponential function which has a horizontal asymptote, and anything raised to the 0 power, if that is 0, then the whole thing equals 1. So because I have that point 0, 1 and there's a horizontal asymptote, that tells me that this is an exponential function. And then for the last two, remember that I have not used b, which was the quadratic, y equals x squared, and I have not used c, which is the square root of x. So in this first one, it's a parabola. This should be so easy at this point that you should know this shape. This is clearly y equals x squared, and that was option B. The only one that's left, of course, will be for this one, but let's just talk about y. It looks like half of a parabola turned on its side, and of course that would be a square root function. So the only choice that was left was C. That's it. Please, please, please write down any questions that you may have had during this video and let me know tomorrow in class, because that's what it's going to be all about. Study hard and good luck on your test that you're working for on Friday. Bye!